respect, but it's better. So anyways, I was saying this, the signal that we do receive, since we're moving with respect to the signal, we don't receive that nearly pure tone. We receive a signal that is actually modulated in frequency, and it will present a yearly modulation. That's the Earth motion around the sun, plus if you zoom, a daily modulation, which is due to the spin of the Earth around its axis. And not only that, it will also actually be amplitude modulated, because our detectors are not equally sensitive to every point in the sky. And so as they move with respect to a fixed point in the sky, the sensitivity with which they will be responding to a signal is different. So this is actually not a perfectly sinusoidal signal. And so, so if we assume that we want to try different sky locations, I just say, well, let me imagine that the sky position from which the signal is coming is that one. So now I know the sky position, so now I know how the signal would be would present itself, what type of Doppler modulation it would have at any given time, because I know our relative positions and relative velocities. So I can just correct the data to make it sinusoidal, and then I'm back in business, because I take an FFT square, and the longer the baseline of my FFT, the better, for the reason we saw before. Okay? So it's actually a little bit more complicated than this, and you can read this paper, which has a bit of math, but it's actually a really nice, simple derivation to follow, because you've got to take into account the fact that there's amplitude modulation, that there's actually two polarizations, but really, this is the basic idea. But there's a problem with it, and the problem is that as we move around the, our detector moves around the sun, so imagine there's the sun here, and we want to make this observation over many, many months, perhaps a year. It's like as if we were combining the data from many telescopes, right, that have a baseline, which is basically the radius of the Earth orbit around the sun. So this is the concept, basically, of aperture synthesis for radio telescopes. And so you understand there that the resolution here becomes very quickly very, very high. And so it means if we want to play this game of doing the correction for each possible sky position, I quickly find out that if I'm observing over very many months, actually, I can distinguish sky positions that are pretty close to each other. I actually have to do this correction many, many times. And how many times? Well, I have the resolution roughly of an arc second or so at 100 hertz. And then it increases with frequency. So when I convolve that with actually having to search for many frequencies, with resolutions now that are typically 1 over the total observation time. So we're looking at 10 to the 7 seconds. That's how many seconds there's in 4 months. Or if it was a year, 3 times 10 to the 7 seconds, okay? With a resolution of, hence, 3 times 10 to the minus 8 hertz, over a kilohertz, okay, times the hundreds of millions of sky positions that I have in the sky, you can quickly see how a search, even without any spin down, covers very quickly many, many templates and becomes computationally impossible if this trick of doing the FFT, I want to do it over months of data. It's just computationally unfeasible. Okay? So unfortunately, we can't use this really simple and powerful approach, leveraging by sheer brute force the power of the FFT at detecting continuous waves. We have to come up with something a bit more complicated, bit less sensitive, of course, to just be able to search this large parameter space. So what we do is we divide up the data in segments. So we don't just do an FFT, okay, a coherent search over 1 year of data. We divide it in segments that are computationally manageable. We do the searches separately on these segments, and then combine the results. So again, whenever I talk about coherent searches, which conceptually are these sophisticated FFTs, I talk about the so-called F statistic, the thing that yesterday, so the number that I got that follows the chi-squared distribution with 4 degrees of freedom is a 2F value. So suppose there was a signal in the data. How would it appear? It would appear like a peak, so like a high value of the detection statistic in each segment. And in each segment, it would be possibly at a slightly different parameter space point. And here, with the height, I indicated the amplitude of the coherent detection statistic in every segment. And here on this axis, just one-dimensional, although we know that it's at least two sky coordinates and the frequency, possibly 4 with a spin down or 5 with higher order spin down, I've just indicated points in parameter space. Okay, so a signal would be a trajectory in this plane. And so when I say I combine the values for the different segments, this is actually consists in figuring out, according to the specific point in parameter space, the specific waveform that are targeting, which of these detection statistic values I should sum up. So the sensitivity of these searches, don't worry, this is the linear SNR, depends on the intrinsic amplitude, and this is, the square root of the noise. It goes, as we expect, like the square root of the coherent observation time, and this is consistent with the FFT idea. You'd seen in the very simple plots that I showed you that was the FFT square modulus that scaled linearly. So now the FFT, if you want, amplitude will go like the square root of the coherent time baseline. And then I gain, let me forget about this W here for now, with the 4th root of the number of segments, which is typical when you use incoherent combination of data. So here you see that the sensitivity goes up if you use coherent time baselines that are longer. In fact, our best would be to have just one segment and all being able to use coherently all the observation time. And unfortunately, though, also the computational cost rises a lot because these searches are very expensive. So if you make this too high, at some point you just can't do the search. Another thing I would like to point out here is that in order to do a search of this type, we typically have to wait until all the data is there. This is because we have to combine over many, many templates all these searches over the entire data set. And there's so many that we can't, do this search for this set of templates when we have this segment, store it, do it for the other 10 to the 17 templates, store them all. Then when the data comes in for the second segment, store these 10 to the 17 and then add them. So we actually have to wait until we got all the data and then parameter space chunk at a time, we can do all the segments. So this is the reason why typically when you look at the output of scientific papers, LIGO will first have the short duration signal analysis. These can be done in real time. These can't even be started until the end of the run. Okay, so typically they lag about 1 run behind. Now, there's 2 different types of surveys that can be done with this approach. Some are so-called fast turnaround. They're rather broad and robust to possible variations of the signal. I've only talked about signals that are these perfectly monochromatic signals, the stay phase coherent. Well, actually, for some objects, that's not the case. So even though our deepest searches make that assumption in order to make the time baseline that is coherent as long as possible, to dig as deep as possible, it's good to have methods that trade off robustness with sensitivity. Okay, so we have two approaches, these very broad parameter space, less computationally intensive, so fast turnaround and robust, with more limited in breadth, but really the deepest that we can do type of surveys. And even if one of these types of surveys is significantly less computationally expensive than the other one, you shouldn't imagine that they're actually cheap. They're not, even these, they're not things you can do on your laptop. These are searches that require large computing clusters, and they take weeks to complete, okay? And we're talking about on several thousands of CPU cores. And the really computationally intensive ones, they require distributed volunteer computing projects like Einstein at Home, where we leverage I think this number is wrong, where we leverage the computing powers of hundreds of thousands of computers. So here you have two references for these two different types of surveys for most recent papers. And I'm going to concentrate a bit on this because this is actually what I do. So I'm going to tell you a bit about Einstein at Home, about the fact that actually the noise is not Gaussian, and so we actually have to deal with this. This is a big problem. And show you some results, and so how one then can interpret them. Because when they come from large parameter space searches, they're a bit more involved to interpret than when you interpret results from known objects. So let me start with Einstein at Home. As I said, this is a public distributed computing project. You might have heard about SETI at Home. Has anybody? So this is a search for extraterrestrial intelligence. It's the first type of these projects. Was started by David Anderson, who got a grant at Berkeley, and then he actually went on to try and develop a generic infrastructure to try and, promote this as a tool for doing highly intensive, computationally highly intensive science in a broad variety of problems. So he developed BOINC, which is the Berkeley Open Software Computing Infrastructure, and Einstein at Home is one of the main projects that relies on this. And we have to provide support to run on Windows, Mac OS, and like Linux clients, obviously. So the basic idea is that the search that you run on one of these BOINC projects has to be trivially parallelizable. It means you have to be able to divide it in smaller chunks that are completely independent one from the other and can be shipped with all that they need to run, data and your auxiliary file, and then they're sent, the data and whatever needs to be shipped, like the computational task, to the volunteer computer. The volunteer computer crunches and does its task. It typically is supposed to run for a few hours, a few to several, 5 to 12, depending on how capable and fast the host is. And it will kick in when the computer is left on but inactive. And then the host sends the result back, we get them, and then we obviously analyze them. Einstein at Home is not a sophisticated Ferrari. It's really a heavy lifting machine. And so we have to choose carefully what we put on there, because there's, it's a big job to deploy searches on this, and there's a certain inertia associated to just getting a whole search started, all the data distributed to the mirrors, and then the mirrors distributed to the host. It has to be something that keeps the host busy for months to be worthwhile, okay? But that's what we need, heavy lifting, actually. This is to give you a bit an idea of the numbers, of the scale of Einstein at home. And this is what the people get when they actually run Einstein at home. They get this rotating celestial sphere, and what they can see is the place this should be rotating usually. I don't know why the animation doesn't go off, but here they get a marker that shows what direction in the sky their computer is searching at that time. So please sign up and help us find that signal. So anyway, we get all these results back, and each computer, each volunteer computer, as I said, is busy, let's say on average 6 hours. And it looks at something like 10 to the 9 parameter space points. And there's no way we have enough bandwidth to transfer all 10 to the 9 results back. So we actually cut very much on the number of results that we come back, that we allow the host to send back. We tell the host, send us back only your top 1,000 or 10,000 points out of the 10 to the 9 that you've looked at. Okay? And so it's important that the detection statistic that we use is robust to possible artifacts that there might be in the data, like lines and artifacts that might give us high values of the detection statistic while actually being due to disturbance. Because our top list is limited. Our top places to come back to us are limited, and we don't want them to be filled by the junk that's in the data, okay? So robust statistics are statistics that are improved to be robust with respect to the typical disturbances that we find in the data. And that's necessary because the standard coherent statistics, the FFT, assumes Gaussian noise. But its values can be increased due to noise when the noise is like a coherent line, because a coherent line looks more like a signal than Gaussian noise. So it will trigger the detection statistic to give a high value where it's a false alarm. So we've developed a statistic that tests against a composite noise hypothesis. It doesn't test only against the Gaussian noise hypothesis, but the union of Gaussian noise or a line, okay? And this is the reference paper. And I really want to just give you an idea of it, just to, make you aware that one has to go one step further. Great, this tells me I have 15 minutes. One step further when you actually analyze real data than the perfect noise case. And so we actually compute, rather than the standard likelihood that tests the signal hypothesis against the Gaussian noise hypothesis, test the signal hypothesis against the Gaussian noise or line hypothesis. I don't have the time here to go into the details, but I want to show you the performance of the different statistics. So we go back to curves that are a bit some of the curves that I hinted to when I was talking about comparing the performance of different detection statistics at the beginning. So on the left side here, you find, as a function of frequency, snippets of the spectrum, the normalized spectrum of the data for the two detectors. I think Livingston in red, Hanford in blue, but this is completely unimportant, which is which. The point is that here you see this is basically a well-behaved stretch of data, okay? And here what you have is at fixed false alarm, as a function of signal strength, the detection efficiency. And please look only at the red line with the star and comparing with the blue. And you can see here that in fairly behaved noise, the robust statistics that we have developed has a performance that is comparable to the standard statistic. And this is what we want. We don't want something that performs well when there is a line, but then when the noise is okay, actually degrades the performance. Obvious, but to be checked. Okay, here's instead a case where one detector has noise that's well behaved, but the other one has a coherent disturbance here. Okay? And this is a situation where when you look at the detection efficiency, the standard detection statistic efficiency is degraded respect to our line robust detection statistic, okay? Because if you fix the signal strength, the detection efficiency of the standard statistic is about 40%, whereas it's higher than 80% for the new detection statistic. So you see, these are, it's really important to develop statistics that are robust, because what it means is that your detection efficiency is safeguarded even when you have noise which is not so well behaved. Mm-hmm. You'll just be less sensitive. It's basically, there's nothing conceptually different in using one detector or two detectors. You can just see two detectors as a single detector with a strange arm configuration. It's like having 1 month of data 1 day or 3 years is again just a strange detector, right? Combining just more data. Same if you add detectors. So these are just examples that show how the detection statistic perform with different types of disturbances. So we don't have a lot of time, and there's nothing really doesn't add to the concept. I'm going to move on. And I want to give you the idea that it's important in the real data to move beyond the naive Gaussian noise hypothesis, okay? And I've also told you that this is important because Einstein at Home returns to us, the people who do the data analysis, only the top candidates. And so we don't want these to be polluted by the garbage. And I want to show you, though, visually how this actually performs. So when we get all the results, the first thing that we do is that we gather them in 50 millihertz bands. So we put all the results that come from all the sky positions, but from the same 50 millihertz band, all in the same pot. And then the first thing we do is that we plot them all as a function of frequency and frequency derivative. And here is the detection statistic, which is also color-coded, okay? And so this is an example of a band where there is a clear disturbance. And this is what happens when the detection statistic that's used for ranking is the naive FFT, the 2F statistic, the one that compares the signal hypothesis to the Gaussian noise hypothesis, okay? It lets through, obviously, these very high detection statistic values. But are these really signals? Well, let's see what happens if we compare it with what we get back when we rank our results with a statistic which is robust to lines. Well, we see here that the amount of parameter space that's affected by these increased values is smaller. And here's what happens when we use an even more sophisticated robust statistic that not only it is robust with respect to lines, but also to transient lines, okay? So we actually understand here that what was causing the problem was not just a line. It was actually a line that was only one detector and only for a short period of time. And a specific statistic that is designed to catch those type of disturbances and designed to suppress them returns a top list that now has different parameter space points. You see, this only shows you f and f dot, but here I get contribution from all sky positions. And the point is that here you're getting different parameter space points, even though they have similar values of f and f dot, than the ones you were getting here or here. Okay? So this actually changes your top list. It's really important to have these robust statistics, robust with respect to the type of artifacts you have in your data. There's no way around. You've got to know your data to understand how to build stuff that's robust with respect to the typical contaminations. Well, we characterize the performance of our detection statistics with injection and recovery Monte Carlos, and whose results are then summarized in those like rock curves that I show you. At at this signal strength, this statistic has a detection efficiency of 95% or so. That's a very important thing, of course, that we do. Still, even being very clever, there's still stuff that just evades, that clearly looks like a disturbance, but has passed through all our detection, or our clever detection statistics. And so a good example was the first Einstein-Sohm search that we run on the O1 data that was a really low frequency. We concentrated with really long coherent timelines. 210 hours is really long. It's nearly 10 days. It's a huge coherent segment length. And we could do this because we were looking at low frequency, where the sky resolution is relatively low. Okay, so the computational cost of looking at the sky was not too high. In spite of having used all these clever statistics, this was the distribution that we got. This is a histogram that basically shows as a, well, you could say this is the detection statistic. It's actually the p-value associated with the detection statistic for the loudest, for the most significant candidates that we found in half Hertz band. So the detection statistic increases in this direction, and this is how many we got. Okay, this is the same plot, but for another search on other data. And these are our results, and these are our expectations. For that search, these are the expectations, and these are the results. So you could see that for this specific search, all that I want you to get from this plot is that the data was not at all distributed as we would expect it if the noise was Gaussian, or if we had tamed the non-Gaussianity and the disturbances with these robust statistics. So what do you do then? So, well, you still set a threshold, a detection threshold. And this is a histogram that shows how many candidates we got on a certain region of parameter space as a function here of a detection statistic. And we set a threshold here, which is not really a detection threshold, right? Because look, just in this band, we've got all the stuff above the threshold. We don't believe these are signals. So it's not a detection threshold above which, if something is found, we will believe it's a real gravitational wave. It's just a place where we set a threshold for further inspection. With a threshold here, we would have expected, if the noise had been well behaved, of order 2,000 events, okay? 2,000 points. We got 15 million. Okay, so yeah, the noise was very disturbed. And so what do you do then? Well, you do what you do when you want to dig in the noise. And so you say, well, okay, we started with n segments spanning m hours. And we've got 15, we had 10 to the 17 templates that we searched. From these, we pick the top 15 million. And these 15 million, which are now a much smaller parameter space set, we actually look with segments that are twice as long and half each and a total of half the number of segments. So this is a search that concentrates more computing power on the selected points that we think are interesting. And then we put a threshold here, a detection threshold, and the ones that survive this get passed to this, where we concentrate, on the surviving candidates. Again, a search which is more computationally expensive still, so now going up to 4 times the initial coherent segment length on now 1/4 of the segments, until we go down on a small fraction of the parameter space, which is only the few parameter space points that survived up to here, and on these we do a fully coherent search, which is now feasible just because we got fewer points in parameter space. So visually it's like a zooming technique, and at each stage, if we had a candidate, since we increased the time baseline of the coherent segments, its significance would increase, and we get rid at each stage of more and more noise candidates. So this is the story for this search. We started with 15 million candidates. We actually did a little bit of magic and brought them down to about 36,000. I don't want to talk about this because I don't have time. The first coherent follow-up that more than doubled the coherent segment length brought them down to about 15,000. The second follow-up, which was now a bit more than double this, brought them down to 8,500. And this, that was the fully coherent search, brought them down to 6,350, which is still a number that's much larger than 1. So here we were a bit stuck, because now we got 6,500 candidates. We've used all our coherent observation time. What do we do? So we actually had an idea, which is actually quite simple. This is one of the candidates, one of the 6,000 candidates. And this is where it was. This is frequency, and this is the detection statistic, okay? And this is where this candidate was. It was 46.95 something hertz. And this is the value that we got from a multi-detector search, fully coherent. We thought, okay, let's redo the search, but this time, in our search, let's switch off the Doppler demodulation. You remember, you have a sky position, and what the coherent search does, it now brings back the signal to looking like a sinusoid, which doesn't look like a sinusoid because it has the Doppler modulation due to the relative motion of the Earth around the sun and around its spin axis. So if this is a disturbance, it's more likely to not have that type of modulation, which is obviously astrophysical in origin. So it could be that we're having an increased value of the detection statistic because it might be coming from a sky position that has a weak modulation. But if we actually remove it, we might actually see that it increases rapidly. The significance actually increases. And so this is actually what happens to it when we do this. So if we rerun the search just for this parameter space point, with the Doppler modulation turned off, we actually see that the significance here increases dramatically. And so we actually managed to develop a veto based on this idea, on the comparison of, the idea is if when you turn the Doppler modulation off, the significance increases, this is likely to be a disturbance. And so with this idea and this veto developed, a little bit more, there's a whole bunch of details, but that I'm not explaining, but this is the idea. We managed to go from 6,000 surviving candidates to 4. And we believe this veto is safe, by the way. We checked that it wouldn't accidentally remove our signals. And so these were our 4 surviving candidates. And so what do you do? Well, of course, you put them in the paper. And then, since by the time we finished the search, we actually had 4 months of data from the next run, we thought, great, it's another run. let's follow them up. Now we know their parameters pretty well, and we see if we can actually see them in another data set. And so this is what we did. And so we did directly a coherent search over 2,000 hours. And we searched an area, obviously, around the nominal parameter values, because these parameter values have uncertainties. And we compare what we found with what we expected. So for each candidate, we expected a value of 2f if it were due to a signal that is plotted here with a certain variance. This is the value that was recovered, and this is the value that was expected on that search if the candidate had been due to noise. And unfortunately, all of these candidates were ruled out. So that's how the story went. And I think if you now read the paper, you'll actually be able to follow it. And there's a lot more sort of detail. But I believe that, you know, if you've understood what I've said up to now, you'll find it a lot easier to understand the paper, or a whole bunch of papers that are similar in scope to this, even though the details might be different. So we didn't detect anything. We set upper limits. And now upper limits are, again, 90% upper limits on the gravitational wave amplitude for signals from anywhere in the sky at this frequency. And here are our results from the Einstein at Home search compared to the broad surveys. They're a factor of 2 or more constraining. And they can be turned in upper limits, again, on the ellipticity. But now, remember, we're doing a broad, blind all-sky search. So these are upper limits as a function of the signal frequency on the source ellipticity. But since we don't know the distance of our source, we have to parameterize them, assuming different distances. And so this is how you read them. Suppose there's this point here. Here it says basically that we can exclude objects with ellipticities that are greater than about 10 to the minus 5, which is a perfectly reasonable number, within a distance of 100 parsec from Earth at frequencies greater than 60 hertz over the entire sky. Okay, so this is now the type of statement that you're making. You're making a statement about the population of objects out there. And I want to show you results from another search. This is a broad, fast turnaround search, because these scope higher frequency ranges, and so they scope ellipticity values that are a lot lower. And now here, you can exclude objects with ellipticities higher than 10 to minus 6 out to 100 parsecs with frequency higher than 200 hertz. So you see that even in these broad all-sky surveys now, not just the point objects you know, but any objects out to a certain volume, you can actually exclude the presence of objects with certain ellipticities. So I've gone a bit fast here, but I hope it was relatively clear. And I want to just quickly recap. Today we talked about the difference between different types of blind surveys, the challenges of blind surveys, Einstein at Home, the importance of robust detection statistic, multi-stage hierarchical approaches, these zooming techniques, the type of things that you have to come up with if after you've done a whole multi-stage you're still left with a lot of candidates. Sometimes you just have to invent things on the spot to try and solve problems. And I gave you an illustration of recent results, and in particular, sort of the astrophysical reach for these types of searches. So I hope this was helpful. Thanks. And I'm now 5 minutes late, but yes. Mm-hmm. Yes, yes. But, mhm. Well, that's a good question. Um, One would start a real comprehensive hunt of the instrument to figure out what type of coherent disturbance could be in the data. That's that's the reality of the fact. The point is that we've actually never encountered a situation like this. And let me also say something which might be more convincing, in fact. These are the measured values over a certain data set. So you have to ask yourself what these frequencies mean. Okay? These are the signal frequencies. What's the signal frequency if the object actually spinning down? So there is a tag I haven't talked about. There is a reference time that defines what these frequency values mean. And typically that reference time is chosen to be close to where the data is that refers to this analysis. So when I look at data from another run and have to look for a signal with this frequency and the spin down value, and there's been a gap of a year between the two observations, I have to imagine now that that spin down here has acted for 3 times 10 to the 7 seconds and moved this frequency value to another value. So the disturbance in my detector not only has to continue to behave over a different period of time, exactly like this astrophysical signal, but it also has to have evolved in the time between the two data takings, like that signal. So at that point, if it quacks like a duck, if it walks like a duck, it's a duck. We'd need anyway to look at the detector very carefully. This is a very difficult question because I could give you the p-values associated to the last search that I did, the last fully coherent search over a very small parameter space. But is that an interesting p-value? Because actually these 4 candidates were arrived from a long chain of searches. And so they actually have a very low p-value for the single template search, but over 10 to the 17 templates, their p-value is very hard to determine in reality unless you assume Gaussian noise that this noise doesn't have. So a big problem of this type of searches is exactly to determine the p-value, because we can't do, like for the CBC searches, time shifts produce many realizations of our experiment and then see where our measured point lies with respect to this background. Because it's hard enough to do one search over 10 to the 17 templates. How are we ever going to be able to simulate our background over so many trials? So the real honest answer is that I could throw Gaussian p-values around that I don't believe and answer your question. The real answer is that we don't know what the significance of these are. And this is why, in fact, I think that if we ever detect a continuous wave signal, we'll have to do something like this. This is what we arrive at from a data set, and then we'll look at another data set. There, the search will be much more limited. We will be able to estimate the background, and there I can give you a p-value. Okay. I think then we're done.